This is John Griffin calling from Modelon AB, and today I'm going to talk to you about Modelon's Vehicle Dynamics library. First, I just want to introduce myself. I'm John. I'm a simulation engineer here at Modelon. My experience, I've been with Modelon since 2011. Have 4 years experience working with the VDL. Prior to coming to Modelon, I had 10 years experience working in NASCAR motorsports. And much further ago, previously, I was a product manager and lead developer of Adam's Car. So today's agenda, basically, we're going to go over what is the VDL, try to talk about some of the key benefits, go through the library contents, focusing on some of the later features or most recent features, and then go through a use case on drivability and modeling drivability with the VDL. So what is the VDL? Well, the scope of the VDL is to provide an environment for design and analysis of vehicles and vehicular components. So in order to do that, the library contains all the components necessary to model a vehicle. So you've got suspensions, driveline components, engines, transmissions, capability of modeling hybrid electric powertrains. You can model aerodynamics. You can model driver interaction with the vehicle. Model ride elements such as springs and dampers, and of course tire-ground interaction, and also hook up the vehicle to typical automotive ECUs through controls. So given all these components, the scope of the library is actually really broad. The library can be applied to standard passenger cars. It's applied in motorsports. There's components and applications for heavy trucks, military, and also construction equipment. Beyond the standard scope, beyond the original scope of looking at vehicle dynamics, you also have the capabilities of looking at other things such as active safety, driveline dynamics, engine vibration, ride, traffic interaction, and then components themselves through component testing. The key benefits to the VDL are first and foremost, it's open code, so it allows users to go in and view, extend, and modify models. And it's been stated that having open code provides the same advantages as basically an in-house tool. So here you've got a commercially developed tool that a customer can have access to, and it's open enough so that it feels like an in-house tool. Another benefit is it's scalable. Users can work at either the microscopic or macroscopic level, so either the component or system level, which allows experts to focus on their expertise. It also helps the VDL fit anywhere in the tool chain. Another benefit is its flexibility. There's basically no limit on the configurations that you can build. You can model typical 2-axle car, or just keep adding axles and end up with a 4-axle military vehicle. This makes it easy to design and evaluate innovative and non-traditional concepts. Further key benefits is its multi-domain capabilities. The multi-domain capabilities allow you to get a better understanding of the complete system behavior. It also provides a direct interface for ECU design, your ECU design tool chain, and makes it easy to integrate electrical, hydraulic, and pneumatic components. And another benefit, which I have a lot of points for because I think is a huge differentiator for NON-DYMOLA and the VDL, is its deployability. It's deployable. There's multiple options for deployment. These include binary export, source code export, and FMU. Deployability makes the distribution of models and analysis possible across an entire organization. It allows you to use the VDL models in other environments such as software in the loop, hardware in the loop, and human hardware in the loop, or driving simulators. It also allows you to safely share models with suppliers through encryption or sharing as an FMU. And finally, it allows you to interface models with third-party solvers. As I said, I recently joined Modelon, and prior to Modelon, I worked for a motorsports team. And in that team, we were heavily invested in simulation. And 4 years ago or 5 years ago, we started looking at other possible tools to replace what we had in our tool chain. The problem was, due to budgetary constraints, is that we had numerous tools. We had a very disparate tool chain. We had one tool and basically one license to perform vehicle dynamics with another multi-body solver. And we had numerous specialized tools with a lower entry point and lower fidelity to look at things like suspension characteristics. We had programs to look at different the shock data. And one of the biggest problems with having these numerous specialized tools and this disparate tool chain is it was extremely difficult to share data and actual models. So effectively, it was a dysfunctional tool chain. So when we started looking around at different solutions, we came across the NON-DYMOLA solution. And what the NON-DYMOLA solution provided, it provided one tool and one set of models. So because of its scalability, we were able to, with NON-DYMOLA and the vehicle dynamics library at the core, able to do vehicle dynamics and suspension characteristics in the same application. This obviously, because you've got one model, simplified validation, so you could have your suspension expert work at the suspension level and apply that suspension directly into your vehicle dynamics model. And also, since you had one tool, data sharing became very easy. Another nice aspect about NON-DYMOLA is its scalability. It makes it the scalability makes it easy to work at the component level and move up in system complexity. So you could start at the component level, move to a quarter chassis, a half chassis, full vehicle, and ultimately your ultimate system of a full vehicle. From a scalability standpoint, it makes it very easy to work from the component design and work with that component in multiple contexts. So you can work at the component design and then move on to component test, and then take that component and drop it in a more complex system for like a quarter car for more system level analysis. In order to facilitate working at the component level and moving progressively on, we have rigs at every level really throughout the VDL. So it allows you to look at specific characteristics for individual components, such as springs and shocks, quarter car steering, suspension, tires, brakes, or engine. And then ultimately also do constraint rig testing on your chassis. So there's 4 post rigs, 7 post rigs, rolling road rigs, and a corner solver to look at vehicle states. The library contains all those things that you need to perform chassis handling analysis. So within the chassis, there's different suspension models and suspension components. In the powertrain, there's the engine, the driveline, the transmission, and capabilities to do hybrid electric modeling. There's brakes, there's tires and grounds for tire-ground interaction. There's drivers to drive the vehicle. There's active safety components, and there's also the environment. One of the new features that we added in version 1.6 was a data access capability. When I first started using VDL, it was one of the things that I noticed was difficult to do was to actually get external data into the application. So what Modelon did is they developed this generic data access facility, which allows you to easily parameterize components to external data sources. So there's utilities for both reading and writing of data. And the nice thing is that it too is flexible. So it provides custom data hierarchies that are independent of model hierarchies. It's extensible to be compatible with virtually any data format. By default, it comes with XML, so it's configured to work with XML data files. It's easy to modify data without recompiling the Modelica code, which is very important from the deployment standpoint. So the good thing is data access provides a consistent way to change model parameters in exported models, regardless of how they're exported. So as you can see below, what you do is you parameterize a model using the data access calls, and then you can modify the parameters at the file level, and then resimulate your model without recompiling. Another key component to vehicle handling is the suspensions. So of course the VDL contains all the components necessary for detailed analysis of suspension and steering systems. It contains an extensive library of suspension components, ride elements, including springs, dampers, and stabilizer bars, various steering systems. It also comes by default with over 30 different suspension topologies, and those vary in level of detail from planar to tabular to full multi-body. You can also change the type of attachment points to have either kinematic or compliant attachments, and the compliance can be modeled as either lumped or bushings. Also in version 1.6, we added something called switchable attachments and mounts, which basically means of the 30 different suspension topologies, you really have hundreds of configurations. So what I mean by switchable attachments and mounts is it allows for configurable topologies. So as you can see here, switchable mounts basically allow you to identify what the spring or what the damper is attached to. We also have replaceable mounts, so you can change a rigid mount to an adjustable mount. Which gets me to chassis tuning. Chassis tuning is also something that we added in version 1.6. And basically, you can take a rigid mount and add tunable mounts. And what tunable mounts do is basically they allow you to do adjustments on the chassis. So chassis tuning consists of two main components. It's tuners and tunables. Tunables are the things like on the lower right-hand corner, which are the shims, which are actually the things that modify the system. Tuners are the controllers that modify the tunables. So the application for this, for OEMs, is it automates ride height adjustment. So if you change the ballast or the cargo in the car, one of the things that you used to have to do is manually go through and modify spring rates or installed length to get the right ride height. Well, tuners do that for you automatically. The other application is in motor sports. So tuners basically allow you to replicate the physical setup procedure, such as shim adjustments, driver in and out, fuel, and ballast. So to modify your camber shim or your toe shim or your tie rod length to get the desired physical setup that you desire. One of the things that we've seen from this actually is that with deployment capabilities, people have used chassis tuning in the physical setup procedure and done it in a virtual way. And they then deploy these tools to the guys who are doing the physical setup to actually aid in the setup. So they can use the virtual chassis tuning and determine what kind of camber shim they may need to get the desired static camber that they're looking for. Another aspect of the VDL is that it provides for multi-directional design. As I said, there's varying levels of detail in the VDL. So there's different levels of representation for the different subsystems, and especially suspensions. So as you can see in this case, basically you could start with some desired toe and camber characteristics or curves and import those directly into a tabular suspension. Then you could use optimization and go from a tabular suspension to a multi-body representation and ultimately to a physical prototype. Conversely, there's a KNC rig within the VDL so that you can go from your multi-body representation to a more simplified tabular representation if you're looking for better performance possibly. And finally, you can go all the way from the physical model and use a physical kinematics and compliance tests to get back to the suspension characteristics to get into the virtual world. And one of the things that this allows is it allows competitive benchmarking. So basically, you could go and test your competitor's car and then have what the suspension characteristics were of their suspension and not have to know anything about the geometry. Another aspect in the VDL is the ability to model powertrains and the components associated with the powertrain. So we have a package called Drivelines within the VDL, which basically contains all the components and assembled subsystems to model various driveline implementations such as front, rear, and all-wheel drive. And obviously this package, these components are targeted to the development of vehicle drivelines. And in order to properly model drivelines, we have ability to compensate for 3D effects in joints, shafts, and gears. We can get the kinematic and geometric effects in the drive shaft, which allows us to look at reaction torques and forces. The powertrain or the driveline components in the VDL bridge the gap between very detailed subsystems models such as smart electric drive and powertrain. We also have representations of engines in the VDL. So first you have your pure torque map, which allows you to map torque as a function of throttle and engine speed with applications for vehicle handling and drivability. And in 1.6 we had another mapping procedure called pressure map or psychoresolved mapping, which basically allows you to map pressure or cylinder pressure as a function of crank angle, throttle, engine control settings, and engine speed. And the applications here are engine, powertrain, and driveline vibrations, as well as drivability. More detailed engine models, such as from the engine dynamics library, can also be added to study gas exchange and mean value torque production. VDL also contains the required components to model tires and roads and tire-road interaction. So natively in the VDL, there's a few different tire models implemented in pure Modelica. There's the Pajeca 2002, Baker 89, GST 87, RIL 05, and a linear tire model. We also have tire interfaces to other packages such as Delft Tire, so there's an interface for MF Tire and MF Swift. And of course, it's user extensible, either through pure Modelica or interfacing to external code such as a DLL. For the ground interaction, there's different tire contact routines. There's a single point contact model. There's also a geometric and enveloping tire contact model that's available. To facilitate building 3D roads, there's a 3D road builder, which allows you to build closed loop and circuits from a center line. There's also some canned events, such as the ISO 3882 ISO double lane change maneuver, the NISTA fishhook and NISTA J-turn. These two are user extensible, so you can develop your own contact filtering model. And you can also implement your own ground lookup routines. For example, if you wanted to use 3D track data or laser scan track data. The VDL also contains driver models, which will basically allow you to control the vehicle and perform some of these canned maneuvers. So that they're configurable and user tunable. There's a lateral controller, which controls the steering. And there's a longitudinal controller, which steers the throttle, brake, gear, and clutch. And obviously, these can be used in mixed modes. So basically, you've got 4 different modes. So you can use the lateral longitudinal controller in either an open loop or closed loop mode. And finally, there's an event-based instruction driver. The VDL contains active safety components, which is targeted to the development of active safety functions. It provides a platform for complete systems integration. This allows for efficient simulation of the driver, environment, vehicle, and safety system behaviors. It's multi-perspective in that it allows you to use low fidelity models for concept evaluation or higher fidelity models for system verification. Models can then be imported or exported for software in the loop or hardware in the loop applications. And we feel this is an excellent application for FMI. The active safety components are kind of sprinkled throughout the VDL. So in the scenes package, there's components necessary to allow the user to create experiments that reflect different traffic scenarios. This also includes sensors for distance closest to object, relative speed of object in front, road curvature, and distance to a lane border. And also in the VDL, there's different components that have active safety components within them. So for example, you have brakes with embedded hydraulic modulators. And under control units, there's some predefined ECUs and function blocks for ABS, ESP, ABD, traction control, brake assist, and more. So I just want to go through a use case of drivability. So modeling drivability in the VDL. The challenge of OEMs today is to meet increasingly stringent fuel economy and emission standards without compromising customers' demands for vehicle performance. The issues that the OEMs run into is shift performance in field due to increased number of vehicle shifts to optimize fuel economy, vehicle launch to induce vibrations with both conventional and start-stop technology, and driveline vibrations associated with dual clutch transmissions and driveline vibrations. One of the things that make driveline analysis within the VDL possible is configurable model architectures. So with configurable model architectures, it makes it straightforward to switch the context of the VDL to focus on the powertrain. So in the left image, you see a typical vehicle configuration. And in the right image, you see that we've switched around the architecture to be more of a drivability context. And in the case in the right-hand picture, basically the engine and the transmission become in focus. And on the right-hand side, the chassis is represented by a simple load. The common interfaces make it easy to switch between transmission models of varying complexity. So you could switch from the standard VDL automatic transmission model to a more complex dual clutch transmission. they also make it easy to switch between chassis models of varying fidelity. So in the example that I showed originally, there's a simple load chassis, which basically just loads the engine and transmission. Well, it's very easy to go up to higher fidelity models, such as lump mass, swing arm, tabular, and ultimately multi-body models. The lower fidelity chassis models are desirable because the main focus in drivability analysis is straight line behavior and longitudinal dynamics. The other nice thing is they require significantly less information, i.e. the only thing you really need is chassis mass, track width, wheelbase, and approximate spring rates. Higher fidelity detailed models are also important because some launch maneuvers require more detailed models to observe anti-squat and differential and axle wind-up utilities. Some of these different characteristics can be seen by moving progressively from the simple load chassis to the lump mass to the swing arm, tabular, and multi-body configurations. So first we start out with a wide open throttle from launch analysis using the standard tabular engine, tabular chassis, and standard automatic transmission from the VDL. And as you can see on the right, you see a lot of longitudinal acceleration characteristics happening around the shift events. And then what we can do is we can easily drop in a more detailed dual clutch transmission, and you can see the results of that simulation on the right-hand side. So the conclusion, VDL's flexible architecture makes it easy to represent VDL as a tool with a drivability context. And then common interfaces make it easy to perform drivability analysis with components of varying levels of detail. This allows powertrain experts to focus on drivability. Just wanted to go through a partial list of some of the customers that we can talk about. From an OEM standpoint, Audi is using the VDL to work with electrically actuated chassis. Volvo is using it for drivability and safety systems. Tata for complete vehicle design. Daimler is using it for powertrain analysis. And Toyota is using it for drivability and vehicle concept development. VDL is also used in motorsports, in the Formula One series and NASCAR series in North America, as well as motorsports manufacturers and suppliers. And at the end, I've just got a customer reference from a couple of our customers at Volvo. And with that, that concludes the presentation portion. I'd like to move on to the demo. Okay, so the vehicle dynamics library contains all those components that are necessary to model a vehicle and perform simulations for chassis handling. So if you go and look at a typical model, you've got the chassis, you've got an atmosphere which allows you to provide atmospheric effects to the engine and aerodynamics. You've got a ground model for tire-road interaction, and you've got a driver to actually control the vehicle or excite the vehicle. As you go through the VDL, you'll see a list of, it's kind of a top-down approach. As you can see on the right-hand side, there's a typical environment to do a chassis, to do a handling simulation. So in order to do that, you've got your atmospheres, your drivers, your grounds, scenes for active safety, and also your vehicles. As you dig down in the VDL, you'll see that the structure is fairly consistent. Basically, we try to always have interfaces, which basically describe how that particular component interfaces with other components. So it defines the connection between two different components. You've got templates, which are baseline configurations, are runnable models. Then you've got experiments, so you've got sample experiments that can be run by the user and modified by the user to meet their own needs. And then further, you've got all the components associated with that, all the different subcomponents associated with that particular component. So within the vehicle, you've got brakes, chassis, control units, dashboards, and powertrains. Within the chassis, you've got all the components associated with chassis. So you've got bodies, couplings, so you can model heavy trucks, frames again for heavy truck applications, sensors, different suspension components, including the linkages, stabilizers, steering systems, and stub frames. And again, a bunch of different examples on front suspensions, rear suspensions, single axle and twin axle suspension characteristics. one of the things that I talked about in the presentation is the ability to model and do simulations at the component level and test at the component level. So basically, as you dig down into the VDL, you'll always see an experiment subpackage, and within that experiment subpackage, you'll see example experiments. So in this case, I've got an example experiment of a suspension in a rig. So this allows me to look at the suspension and do detailed analysis and design modifications of the suspension before I actually put it in a chassis. So I'm just going to go through and run a simulation quickly. So here's just an animation of the suspension in a rig. Then, of course, I have the ability to look at and plot at different suspension characteristics. So what we use in the VDL is we use variables called summary variables, which make it very easy to find the characteristics that we're interested in. We also typically add commands that allow you to easily visualize the model or run typical plots. So in this case, what I'm going to do is I'm going to go through from a detailed model. So basically a vehicle that's got a tabular suspension in it, and I want to go to a more simplified linear representation. This also demonstrates the data access capabilities. So the first thing I'm going to go through and do is I'm going to run this experiment called parameter identification. And basically what it's going to do is it's going to identify the key characteristics of that vehicle and characterize them to be used into a linear representation. Okay, the simulation's complete, and one of the things that you can see in the output window is the linear single-track model parameters that are generated from this simulation. We can also go through and look at the actual test. So here you can see we're driving the vehicle along the road, and we're exciting the vehicle as much as possible to try to be able to capture the characteristics of the vehicle. Now I showed you the message window where the linear model coefficients were written, or parameters were written to the message window, but they were also written to this external file, an external XML file. And now I'm going to go through and I'm going to look at the linear representation of the system run in parallel with the complex representation of the system. And what you can see if you go into the linear representation of the system, you can see where the model has been parameterized such that it gets its values from an external XML file. Now if I run the plot command, what I can see is a cross plot of the detailed chassis model in comparison to the linear model. So you can see that the parameter identification worked extremely well, and the linear model can actually do a fairly good job of representing the chassis characteristics. So an application, or a typical application of this, would be using the linear model in an active safety application. So one of these type of applications would be such as a traffic simulation where you look at vehicle interaction, and you're less interested in the actual chassis handling characteristics. Sorry, I need to build my road. Now this is also something that's very unique to the DYMOLA and the VDL, is the ability to model more than one vehicle at a time. So there you can see how the vehicles interact with each other. And basically what that is it's there's an active safety component which is demonstrated by the cone, which is a cone of vision. So as the vehicle approaches the vehicle in front of it, it will slow down or apply the brakes. I thank you for your time, and I hope I've demonstrated the capabilities of the VDL. And go back to the first slide. My customer or my contact information is up there, so if you have further questions after this WebEx, then feel free to contact me.